Okay, this is Giancoli Physics AP Edition, 7th edition. We're in Chapter 10 Fluids. We're working on problem 17. Let's go ahead and jump in. That problem reads, a house at the bottom of a hill is fed by a full tank of water 6 meters deep and connected to the house by a pipe that is 75 meters long at an angle of 61 degrees from the horizontal, and there's a figure 1049 to illustrate. Determine the water gauge pressure at the house, A, and then part B, how high could the water shoot if it came vertically out of a broken pipe in front of the house? So go ahead and wrap your brain around that problem to come up with a plan. Pause the video, come back when you're ready. Okay, so our general problem solving strategies is to identify the quantities we're working with and see what we can work with here. Now, the nice thing about this problem is all of the quantities are labeled on the diagram, which helps. But essentially we're dealing with some linear dimensions. Some of them are angled. But we essentially have some height here. They're asking us about pressure. Specifically, they're asking about gauge pressure. Right there. If we take a look at the equations we have to work with in fluids, we have these two different versions of pressure and height over here. Now they're asking us about gauge pressure. So the idea here is you have atmospheric pressure pushing down on the water at the top of the column of water up here in the water tank, but you also have atmospheric pressure down here at the house. By asking us for the gauge pressure, they're asking us to ignore that. They don't really care about the total pressure. They're just looking at the differential pressure between these two locations, because that's going to drive the dynamics of this problem. We're just going to look at the gauge pressure. So we're going to use our equation over here. Calculate the gauge pressure at the house. Now that equation is already arranged so that we can use the numbers we have. The only slight catch here is this height is the total vertical height, which would be from here to here, which is going to be a segment addition of the 6 meter water tank plus this, we'll call it a y value for now, because the height's going to be the combination of those two. Given that this is our angle, we'll use theta for that. And the 75 meters is a length of the hill there. The sine of the angle is the opposite over the hypotenuse. We write that down. So if I want this y value, this vertical value, it's going to be this hypotenuse times the sine. So for this height value here, I can replace that as I plug in my numbers. Density of water, you can look it up in table 10.1 or look it up on the internet. At this point, if you've been working with this for a while, you may already know that number, but it's 1,000 kilograms per cubic meter. If we're on Earth, our acceleration of gravity is 9.8 meters per second squared. And again, our height here is going to be a segment addition combination of the 6 meter water tank plus our length times the sine of the angle to give us that vertical height of that hill. That's going to be 75 meters times the sine of 61 degrees. Okay, so for our mental math here, if you know how to do rough trigonometry without a calculator, the sine of 61 is going to give you about 0.85-ish. If you multiply that by 0.75, just kind of doing a swag of taking 15% off that, just call it 65 for a nice even number. Because when you add that 6, it'll give you 70. So just call this, they'll give you 71. Just call it 70 for a round ballpark number, about 70. That's 1,000. That's roughly 10. So you're looking at about 7 times 10 to the 5th is your final answer. So go ahead and pick up your calculator and see what you get. So your calculator should have produced a number in the vicinity of 7.0165 times 10 to the 5th. So remarkably close to our mental math. Always nice when that works out that way. Now we got kilogram meter per second squared between these two. That's our Newton. I've got cubic meters down here with a meter up here in the numerator, so that's going to cancel one of those, which is going to give me newtons per square meter, which is our definition of a Pascal, so the units work out. That's going to be our gauge pressure. Again, using an appropriate number of significant figures. Looks like we're working with 2 up here in all these numbers. Let's go ahead and round that gauge pressure to 2 significant figures of 7.0 times 10 to the 5th Pascals. That'd be your answer for part A. Now, part B, we don't have to overthink it. Asking how high the water would shoot if it came vertically out of the pipe. The short, quick answer is it's going to go to the same height as where it started. The force of gravity and acceleration gives it potential energy up here. And so if it comes out of a pipe down here, it's going to be able to shoot back to the same height. So we just need to calculate that height, which we've kind of done, just not explicitly. So we're going to recalculate this number to get that total height. It's going to be our 6 meters plus our 75 meters times the sine of the angle. And again, we did a rough swag on this before, and we got about 70 meters total between the two of these. So go ahead and grab your calculator and see what you get. And as expected, I get about 71.596 meters. And again, working with 2 significant figures, we're going to round that to about 72 meters. That'll be the height that the water rises. And that knocks out another problem, and we're on to the next.